Hello everyone. In my first lecture on continuity and differentiability, I covered their definitions and some simple applications. In this second and final lecture, I will take up some challenging questions. So let me first of all share my screen with you all. So let me now ask you this really challenging question. It is given that f is a function from say some a minus delta, a plus delta to r, and it is given that this is the limit h tend to 0 of f of a plus h minus fa minus h upon 2h exists, then f is differentiable at a, and the limit also equals f prime of a, true or false. Means, let me elaborate the question. What it is trying to ask you is this, that if there is a function f which is defined in a neighborhood of a, then, and if this limit exists, the limit that is proposed here, that limit as h tend to 0 of the expression f of a plus h minus f of a minus h upon 2h, this exists, then you have to decide whether f is differentiable at a or not. And if it is, then the value is f prime or something else. The second also is a similar kind of thing. As you can see, that if limit as h tend to 0 of f of a plus h minus twice of fa plus f of a minus h over h square exists, then f is twice differentiable at a, and the limit equals f double prime of a, again true or false. So let me first tell you something about what we know. So this, let me change the color in. So what is given is that limit h tend to 0 f of a plus h minus f of a minus h upon 2h. It could have been h also, that's not a problem, h or 2h. So this is 2h, this exists, this limit exists. So it is given that this limit exists. This limit exists. I let me write h. So this limit exists, and you want to find out what about f prime at a. It exists or it does not. So first of all, I will tell you that this question goes against the common sense. You are more likely to think that this will be differentiable, this limit will exist, and so function will become differentiable, which is false. If I say something is false, if I say that a implies b is false, then it means that I need to give you one counter example which will tell that indeed it is false. So because it is false, I will give you example that is called counter example, that is, choose fx is modulus of x. If fx is modulus of x, then limit of h tend to 0 f of a plus h, and choose a is 0. So f of 0 plus h, don't be in a rush, and then upon 2h, let's calculate this one. So that is limit h tend to 0 f of h minus f of minus h upon 2h. Now, by definition, you have taken f of x is modulus of x. So this is limit h tend to 0 mod of h minus mod of minus h upon 2h. As you know that modulus of negative of h is same as modulus of h. So we end up with this. And once we come here, then we find that this limit is limit h tend to 0. So we can write limit of h tend to 0, 0 upon twice of h. This is of course 0. If you are wondering that h tends to 0, remember h is never 0. h is as close to 0 as possible but never equal to 0. Just as x is never equal to a, x can be as close to a as possible. So first of all, I have given you one example. Rather, we will say this is, in maths it is called counter example. So I have given you a counter example for this fact, that if this limit, they said, if this limit exists, then make up your mind about f prime a. You told it is false. So you're saying it is not true. It is false. So it means what you are saying, that this statement is false. And because this is false, so we are giving some counter example, and that counter example was fx equal to modulus of x. Now, my next question would be that how can we repair the argument? Like, what is the closest that we can get? How do you repair the statement? Means exactly what the message is. So in fact the statement is this, that if f is differentiable, at a, then limit h tend to 0, f of a plus h minus f of a minus h over 2h, this exists. Means if f is differentiable, then it exists, and of course then the value equals f prime of a. So the limit existent does not mean that f is differentiable. Rather, if f is differentiable at a, then you know that this limit does exist and equals f prime a. Let me prove it, because I'm saying it is true. So for true example is not enough, we have to prove it. So I will write like this. I will use definition. So my definition says that if I write this one, calculate this limit of h tend to 0, f of a plus h minus f of a minus h over 2h. By the way, this has got a name. This is called centered quotient, means, or centered difference quotient. It is difference, but centered means it is around a plus h and a minus h. The usual quotient is f of a plus h minus f of a over h, limit h tend to 0. This was known as Fermat's. Spelling is Fermat, but it is pronounced Fermat. So Fermat's difference quotient. This is the one quotient we use in definition. Why quotient? Because it is the value of f at 2 points. So it's like f of a plus h minus f of a and over a plus h minus a. So it is called difference quotient. Means the quotient of two differences. The difference of values of f upon the difference of the values of the argument. So this h is nothing but a plus h minus a. So that is the we use in definition. This is similar looking term, but it is called centered difference quotient. It is sometimes called centered difference quotient. Why? Because it is centered around a. See, this lacks symmetry. This has some symmetry because around a, this is a plus h and this is a minus h. It looks good. So it is called centered difference quotient. It's still difference because 2h is still a plus h minus a minus h. And so it is still difference. So it's also a difference quotient, but it is called centered difference quotient. It is called Fermat's difference quotient because Fermat was the one who gave it to us. So now we want to prove that if f prime a exists, then this centered difference quotient, this equals f prime a itself. So we'll play with it. Rather, we'll write limit h tend to 0. I subtract f of a because that is the Fermat difference quotient. So I'll try to bring it in. So then we write f of a minus f of a minus h over 2h. And so I can write this as cleverly as limit of h tend to 0. Let me erase this a little. So this is limit of h tend to 0, f of a plus h minus f of a, And here I may write like plus f of a minus h, or let me just erase this. So I can write this over 2h and plus, note it carefully, and this is f of a minus h minus f of a and over minus 2h. Make no mistakes about it. This is what we have written. This big thing. Everything matches. Everything agrees. You see, this is negative. So this negative will take care of this negative. It will make it positive. And this negative will send it here. It will still be negative. So we are good. Now I can break them. So I'll write half is outside. Limit h tend to 0. F of a plus h minus f of a over h, and plus limit of h tend to 0, f of a minus h minus f of a over negative of h. So now the careful reader might have noticed the introduction of negative h, and you will not wonder. So now this is half of, this is nothing but f prime plus a, because it is the right hand derivative of f at a if it exists, plus this is left hand derivative of f at a if it exists, and notation becomes f prime negative a. So this is your thing. So it tells you much more. It tells you that if you were given that f is right differentiable at a and f is also left differentiable at a, then the value of this difference quotient will be half of f prime plus a plus f prime negative a. But you are given that f is differentiable. If f is differentiable, then you forget about plus and minus. This all are equal, and the common value only is called, the name is f prime a. So we don't call left and right. It is, now we are calling, it is the derivative of f at a. So it means this becomes half times 2 of f prime of a, and that gives you f prime of a. So we have proved. Let me run through it. It's a beautiful proof. So let me run through it again for your benefit. So we said this, that if this limit, if limit of this one, if limit h tend to 0, f of a plus h minus f of a minus h over 2h, that is, if the limit of centered difference quotient, if this limit exists, then it does not mean that it is equal to f prime a. Rather, it was the opposite way, that if f prime a exists, means if f is differentiable at a, then the limit of centered difference quotient indeed equals f prime a itself, means f is differentiable. Okay, so we just wrote f of a plus h minus f of a because I wanted to form this Fermat difference quotient, and similarly for this one. So this was right hand derivative and this was left hand derivative. So we wrote that this, the limit that you ask, equals half times RHD plus LHD, that is f prime plus a and f prime negative of a. Because f is given to be differentiable, it means f prime plus a equals f prime of negative a equals f prime of a. And so we are good. We got half times to f prime a, that is f prime a. So that's your resolution of first part. That, so let me go back and see again that this is your first part. And so it was this. It was your here. So let me be careful. So this was this. We started our discussion with this one, that if limit exists, then if it's divisible at a, that was false. We repaired the statement by saying that in fact it's somewhat the other way around, that if f is differentiable at a, exists, and its value, the value of limit, becomes f prime a. That's fine. A similar looking thing is the next one, and that one, that if you are going here, so if you are going the second one, if limit h tend to 0, f of a plus h minus 2fa plus f of a minus h over h squared exists, then f is twice differentiable. This also will be shown to be false. This also will show that this is false, means this still is false. So once we are claiming it is false, it means I must be prepared to give some counter example. So let me give you some counter example. And so the it is this, that you have got now f of a plus h. F of a plus h, it has got two things now, f of a plus h minus twice f of a plus f of a minus h over h squared. Now it is h squared, and limit h tend to 0. We will prove that this limit exists. This limit exists does not imply that f is twice differentiable. No, it does not imply. So it is, example will be f of x equal to x mod of x, x modulus x. This is a good one. It builds on what we learned early. So x mod x. Now, as you know, this function is f of x equal to x squared, x greater than equal to 0, and negative x squared, x less than 0. You will find that this f is differentiable at origin because f prime 0 will become 0, but it is not twice differentiable. That we can show now. So now first calculate this limit. So limit h tend to 0, you take f is this, you take a is 0. So this is f of h minus 2 of f of 0 plus f of negative of h upon h squared. That gives you, just like previous problem, as in the last problem, h tend to 0, f of h, that is h mod of h, we are good, minus 2f0 is 0, and this gives you that negative of h modulus of negative of h. So once again you have limit of h tend to 0, h of modulus of h, and negative h of modulus of h, because mod of minus h is mod of h. Mod does not distinguish between negative and positive. It handles them same way. It makes both of them positive ultimately. So now this is h squared. So you are getting limit of h tend to 0, 0 upon h squared, and this number becomes again 0. Again, to remind you that h is never 0. H is as close to 0 as possible, as you may please, but it can never be equal to 0. So we got 0, and so we can say that this statement is certainly false, because fx equal to mod x, this offers what math people called counter example. You want to destroy a claim, give a counter example. If you want to establish the truth of something, there is no other way. You have to prove it. So now let me repair the argument on the lines of the first part. So now we will say that if f is twice differentiable, if a is twice differentiable at a, then limit h tend to 0, f of a plus h minus twice f of a plus f of a minus h over h squared exists. If this is there, then this exists, and you can find the value also exists, and then equals, we will check, equals f double prime a, because f is now twice differentiable. So we can test this. So let us now get to work. We want to find this limit h tend to 0, f of a plus h minus twice of fa plus f of a minus h upon h square. Now, again, I told you, what is continuity? A limit. What is differentiability? Is still a limit. Everything is a limit. That's why we do the chapter limit called first. Okay, so now we want to find this limit. So this form is 0 over 0, because when h tends to 0, numerator tends to 0 and denominator also tends to 0. So we can apply something that is called L'Hopital rule. It is written like this. So it is written like this, or more correctly, it is written is there is no s over here. It is written like this. So it is called. It is written like this, but it is pronounced L'Hopital, just like Fermat was pronounced. It was written F-E-R-M-A-T, but it was called Fermat's theorem. Fermat's, a Frenchman. So here L'Hopital. So we pronounce L'Hopital. So we'll apply L'Hopital rule here, 0 by 0 form. So L'Hopital rule says that if this is there, then let me go to the next step and calculate this limit. So that is, this is question mark, means if this latter limit exists, if this limit exists, then original exists. So now it is given to exist. Now h square, so this is 2h, and this is f prime of a plus h with respect to which I'm differentiating. So this is 0, and this negative will come out. So this is negative of f prime of a minus h. So we got a quotient like this. So if you want this limit to exist, so what I'll say, if this exists, then this also exists. We don't know this exists or not. We are testing. So we are saying that if this limit exists, then this limit also exists. And this exists, we know from part 1. In part 1, first part, we read that if f is differentiable, then limit of h tend to 0, f of a plus h minus f of a minus h over 2h also exists and equals f prime of a. We apply the same thing, just choose your gx as f prime x. So write this limit as, it is like limit h tends to 0. This is g of a plus h minus g of a minus h over 2h. And now we know that this g is differentiable because f is given to be twice differentiable at a. So because g is differentiable at a, so this number just becomes g prime of a, and so that is becoming f double prime of a. So we have proved that if the limit exists, then it has to be equal to the second derivative of f at a. So this answered these two questions. So that was really challenging. So let me now do some other direction in it. Let me go to a new problem maybe. So now we have, now I will apply, yesterday we learned about definition. So let me apply definition to one good question that will be like this, that the question says that f of x, this I use to start a question rather than writing a number. Fx is x tan inverse of x plus sec inverse 1 over x, and then you are given that this is pi over 2, this is this, and pi over 2, x belongs to minus 1 comma 1 and 0 subtracted, the single element, because anyway look at sec inverse 1 over x, 1 over x, so of course 0 has no place, so 0 is subtracted. Minus 1 comes because sec inverse 1 over x, it is defined, sec inverse t is defined only when t belongs to r minus minus 1 1. So it's like this. So for some reason we are defining only in closed open interval, that's fine, that's our choice. And pi by 2 when x equal to 0. And we want to find that, my question is, find first domain of f prime and also expression for f prime as you have found for f. So f is defined like this. You want to find domain of f prime, and also you want to find expression for f prime. Or more precisely, you just want to find this. You can just say that, you can just ask for that f prime 0 exists or not. F prime 0 exists or not, because otherwise it will be, of course, it will be the same domain as domain of f if f prime 0 exists. Okay, so far so good. Now we do like this, that I told you that this we can dealt in two ways. First of all, because f is defined like this, so This is product of two functions which are differentiable in this interval, and this also. So I will first write it somewhat good manner. So I'll write f of x equal to x tan inverse of x, and plus I write it like cos inverse of x. Let me write cos inverse of x. There is no point in carrying sign. See, sec inverse of t is cos inverse of 1 over t. Whether t is positive or negative, I don't care. And of course, t must be defined. Sec inverse t must be such that sec inverse t and cos inverse t both make sense. That is already there. Be careful. If it were tan inverse something t and you want to change to cot inverse of 1 over t, then you have to be careful, boy. It's not always positive or negative. So it depends on whether t is positive or t is negative. So here you have to be careful. Here I can throw all care to the wind and I can just casually calculate x inverse x plus cos inverse x. That's a good form. And domain remains same. This is minus 1 1 and 0 subtracted from it. Here 0 is not present, but 0 was present originally, so still that will be taken care of. Now, and this is pi over 2, that will leave x equal to 0. This is all right. Now what I will do, that I will find f prime x. So let me write f prime x. It so happens that in the interval minus 1 1 0, this interval, this function is made up of differentiable functions. So I can simply differentiate. I will get product rule x times tan inverse x. So 1 upon 1 plus x square plus tan inverse x times 1. And this becomes negative of 1 upon square root of 1 minus x squared. So I record them here, that f prime x is one more step I write. This is by simplifying. So I'll write x upon 1 plus x squared plus tan inverse of x and negative of 1 upon root of 1 minus x squared. That is when x belongs to minus 1 1 0 subtracted. This one, f prime x. X is 0, we do not know from f0. Means we have to calculate. It is not known directly. So there are two ways. One, I apply definition. That is, I apply first principles. You can't go wrong. First principles. Other is, I be little creative, but I have to find out whether I am allowed to be or not. So I can be creative, and I may think that let me calculate limit of x tend to 0 f prime of x. Means that getting f prime 0, I may look at limit of derivative. So limit of derivative at x tend to 0, this we know has some relationship. It has got some relationship with value of f prime 0 under some circumstances. So I can use that. First, let me use definition, because definition you can't go wrong. So I will write definition. So I will write f prime plus 0, means right hand derivative is limit h tend to 0 f of 0 plus h minus f of 0 over h. So that gives you limit of h tend to 0 f of h minus f of 0 over h. We calculate easily. So we write here limit of h tend to 0 f of h. F of h minus f of 0. So f of h, we can check, we can tell you f of h means f of h was this one, h tan inverse h plus cos inverse h. So I can write this as h tan inverse h plus cos inverse h minus f of 0 was defined to be pi over 2. This is pi over 2. So this is pi over 2 and over h. So I can use equal to limit h tend to 0 h times tan inverse of h. And mind you, we know that cos inverse x plus sine inverse x is pi over 2. So if I apply this one, I will get here negative of sine inverse h and over h. If I calculate this limit by separating it, we will get limit h tend to 0 tan inverse h minus limit h tend to 0 sine inverse of h over h. So it means that this limit is anyway 0 because tan inverse 0 is 0. There is no indeterminate form. And this one I told you previously we used also. It's like theta upon sine theta. That limit is 1. If you are wondering, let's put sine inverse h equal to say theta. This becomes theta over sine theta. Theta tend to 0. That limit becomes 1. So this is 1. So this is negative 1. It means we got started with this one f prime plus 0. So we got f prime plus 0. We got this as negative of 1. Similarly, if I write f prime negative 0, means this was right hand derivative at 0, left hand derivative at 0, I will get limit of h tend to 0 f of 0 minus h minus f of 0 upon negative h. That equals limit h tends to 0 f of minus h. Again use the same definition because this definition is true when x is not 0 here. So I can write minus h tan inverse of minus h, or I have simplified and written again here. That was also same. Let me just check for you. Yeah, this one, this I will use. So I can use minus h tan inverse. So I can write here negative h tan inverse of negative h and plus cos inverse of negative h minus pi over 2 and upon negative h. That again gives you limit h tend to 0 minus h tan inverse of negative h. This cos inverse negative h again is negative of sine inverse of negative h upon negative h. Although I can take it out, there is no need. I can write limit h tend to 0 tan inverse of negative h and plus limit h tend to 0 sine inverse of negative h upon negative h. Negative is all right. You can use your negative. That is much better. So I write negative and this I consume here. So again, this number equals 1 and this is 0. So again, answer is negative 1. It means from this and from this one, we get that left hand derivative f prime negative 0 is also minus 1, as f prime plus 0 is negative 1 and equal to f prime negative 0. We say that f is differentiable at origin. Now, my question was that could we have calculated it wisely using this thing? We did first principle. So what about this? Had we got limit f prime x? Because already f prime x we know when x is not 0. So I can use to find that limit. So f prime x is this expression. So I will write this expression again. So f prime x, we got f prime x when x was not 0 as x upon 1 plus x square plus tan inverse x minus 1 upon root 1 minus x squared. If I want to get limit x tend to 0 f prime x, this limit I want. So means I want, so I put x is 0 plus h. So I want limit h tend to 0 f prime of h. That is limit h tend to 0 h upon 1 plus h squared plus tan inverse h minus 1 upon root 1 minus h squared. If you do this, you will get this as 0 first limit, second also 0, and third is minus 1 upon 1 minus 0, that is negative of 1. And even if somebody has chosen to go by this one, simply f prime minus h, you would have obtained the same answer. And so you will say that f prime, this limit x tend to 0 f prime x, even if you take right or left, so this is still negative of 1, And because this limit exists, yesterday we discussed in detail, because this limit exists, this implies that indeed f is differentiable at 0, and f prime 0 also equals -1. If this limit has not existed, it had not existed, then we could have said we do not know. Then we could fall back on definition. But if this limit exists, means if the limit of x tend to 0 f prime exists, it means this is only the value of f prime at that point. And this is a special case. Actually, what it happens that f prime becomes continuous at x equal to 0. That would follow if you could write it in a suggestive way, that limit of x tend to 0 f prime x, if f prime is continuous, then this limit business can come inside. Means limit and function, they can commute. And I can write f prime of, watch it very carefully, f prime of limit x tend to 0 x. Means what I have done is I am saying that if you want to take limit f of something, these two are operators, some operations. In general, in maths, not they commute, they need not commute always. So two operators need not always commute, but under certain circumstances they can commute. We do it all the time in mathematics, matrices or other thing. Some things commute, something don't at all, and something does under certain conditions. So it means if f is continuous, then limit can go inside, it can pierce through this bracket, it can go inside, and so this limit straight goes inside. I'm getting f prime of this one, and this limit is simple 0 only, so f prime of 0. So if f is continuous, it becomes this. Actually, that's the definition. If you remember, limit of x tend to a g of x, if this is g of a, then we call that g is continuous at a. Can't I write it in a suggestive language, that limit x tend to a g of x? If I write g of, watch out, g of limit x tend to a x, what has happened? Just this operation of limit x tend to a, this operation, and g, these two operations have just commuted because g is given to be continuous. If g is continuous, then what will happen is that these thing, so if g is continuous, then you can swap. So you can swap the limit, you can swap limit x tend to ng, or that is same thing as math people have got a name for it, that they commute. The operations commute, and so we are good. So this is a good example. So let me again do this kind of thing and I ask you something. This was that I wanted. In this example, I'm illustrating many concepts. So what I'm asking you is that f is defined like this. So f is so and so for this one, and pi by 2 at x equal to 0. I want to find domain of f prime I want, and also expression for f prime on whole. So first part was not a problem. I wrote first cos inverse x because I like this in comparison to sec inverse of 1 over x. So I wrote f of x, and then I differentiated f prime x in this region because it is made up of so many differentiable functions. So like we say that f is made up of two differentiable functions. Cos inverse is differentiable, and this is differentiable x inverse x at this domain, and so this is differentiable. So we got f prime x here, but f prime 0 we do not know. For that, we can use either definition first principle, or we can use something creative. We can find limit of this expression, because this anyway now we know this. So we can try to find what this limit is. If this limit exists, then we are lucky. We are in good luck. It means that this value itself becomes the value of derivative. Means limit of derivative becomes the value of derivative at that point. So we found first principles or definition, which cannot go wrong. You must try this always. So we got f prime plus 0 by setting up the correct expression, Fermat difference quotient. And similarly, f prime of negative 0, we found they all match. So this is a little calculation, both are equal. And so we said f is differentiable at origin. So f prime x, we can write that negative 1. And other was that directly f prime x is given. I can find this limit. This limit happens to be negative of 1 because limit of derivative exists. So that tells you that because limit of derivative exists, then this itself becomes the value of derivative at a. And so indeed f prime 0 is negative of 1. And the upshot is, or the takeaway is, that f prime becomes continuous at x equal to 0 if this kind of thing happens. It does not happen always. We have seen examples day for study. And so here I told you one more thing, that it is not surprising, because once something is continuous, then for a continuous function, the operation of limit and the operation of composing f, these two can interchange, they can commute. You can swap them. So we wrote that, okay, we wrote the definition of, we wrote this definition of continuity in a very suggestive form, writing like limit of x tend to a g of x is g of limit x tend to a x, and then we are done. That was a long problem. So let me now go back, or let me go to the next one. There is no going back because already we have done this one. Nothing to address here. So let me go some other problem and let's see how you fare. So a new problem starts now. Here we are going on a different track. I don't want to spoil the fun, so let me write the problem first. So f of x is a times a square root of x minus 1 plus b times a square root of 2x minus 1 minus square root of 2x squared minus 3x, 2x squared minus 3x, and then plus 1. The reader would note that x minus 1 and 2x minus 1 is the product, and this equals 2x squared minus 3x plus 1. So this is just one thing that comes to our notice when you do this. This is fx, and a and b are real number. A plus 2b equals 2. A, b both belong to R. Now you have to prove that f always, so you have to prove that f always has a root in 1 comma 5 interval open for all b, for each b belong to R. Means you have to prove that if f is defined like this, you are proving that f always has a root in 1 comma 5 for all b element of R. Now some word about it. We are going for solution now. So now, because it is given for all b element of R and a plus 2b element of 2, I will expect first a. What is the meaning of a? In maths, a does not mean a is not 1. In English, it might be 1. In maths, a is not 1. We are you are a group of people who use precise language. So a means, in maths, a means at least 1. At least 1. Or you can say some, like that. So you can say that f always has at least one root, or f has some root in 1, or f has a root. So these all, f has a root in 1, f has at least one root in this one, or f has some root in 1 5, they all are equivalent. If has one root, I do not know. We can't say one root. One root is not correct. Okay, now, so when you look at this problem, it is, you can't solve for all a and b. So and then problem does not ask you to solve. They just ask you that whether it has a root in a given interval. Now, which theorem comes to your mind? Whenever, for me, whenever you have to show that some function or some polynomial has a root in, say, p comma cube, pq, then you must find f of p and f of q if f is continuous. So first check this, f is continuous, because f is made of continuous functions. They are all defined for x greater than 1, of course defined, because for 1 this all numbers are non-negative, and so all are defined. And so it is sum of so many continuous functions. So f itself is continuous on the interval which is my concern. So f is continuous. Now there is a theorem called either it is called Bolzano's theorem after it's discovered. So this is called Bolzano's theorem, or it is called intermediate value property, or in short IVP, intermediate value property, IVP for continuous function, IVP for continuous function, for continuous function. Means what we are asking is that we are saying that there is a theorem called Bolzano's theorem, and that tells you that if it applies to continuous functions and intermediate property. So we'll say like this, that suppose f ab to R is continuous. So it is continuous on a closed interval, ab to R continuous. And suppose f of b less than 0, means FAB are opposite sign. Say it may be that FA is positive and FB is negative, or it may happen the other way around, that this is negative, this is positive, so product is negative. So if you are saying that product is negative and if it's continuous, that's the word operating called continuous. If it's continuous, then f has at least one root in a comma b, means there is a point C element of open AB such that f of c equal to 0. In fact, theorem can be generalized also. Marginal theorem is that if f of a equal to k1, f of b equal to k2, and say for example k1 less than k2 something, or not k2, k1 k2, then for all k that lies between k1 and k2, there is some c element of open interval AB such that f of c equal to k. Means what graphically it is saying, that function is continuous if it has achieved a height k1 and achieved a height k2, then height k will also be achieved somewhere, say c. So this rather is maybe misleading, so I will write here a and b. So we write here a and b, and this is k1, this is k2, so k1 k2. So it means once you have attained two heights or two depths, anything, then you must attain every height in between if the function is to be continuous. Continuous is important, otherwise you can make examples in which this will not be attained. And so many times, why? Because function may be this kind of thing. So this kind of thing also may be there. So we will say that it is at least one root. Here we are applying in a particular case. So we will again write this one, f of x, and we will try to find how it works. So your fx was, your f of x, your f of x was a times a square root of x minus 1 plus b times square root of 2x minus 1 minus the square root of 2x square minus 3x plus 1. So what I am doing, that a plus 2b is given to be 2, and of course all are real. I'll write first, that is a equal to 2 minus 2b. Now I'll make what is called casework. This is a technique of maths. Whenever you have got branches, we make casework. We say that, okay, let us divide the cases. Let us divide the problem into cases. So that is casework. We do casework on B, means casework on values of B. That, okay, for different B, let's analyze what it becomes. So if B is positive, or B can be 0, or B is negative, you can have three possibilities. This is the simplest one, is B is equal to 0. So if B is positive, then just check here. if I write f of 1, means evaluate f at 1. So f of 1 is, that is 0, a times 1 is 1, 0. This is b, so this is b, and this also is 0. So at x equal to 1, at x equal to 1, at x equal to 1, this is 0, this is 0, this is not 0. So it means f1 is b, so f1 is positive, f1 is positive. If I want to find f of 5, so f of 5 is, this is a times root 5 minus 1, so that will give you twice of a plus 3 times b minus 6. Why 6? Because see, root x minus 1 at x equal to 5 is 2, root 2x minus 1 is root of 9, that is 3, and square root of 2x square minus 3x plus 1 is product of these two, so that is 2 times 3, that is 6. So we have not made any calculation mistake. We have done f of 5 is 2 plus 3 minus 6. Now because casework is on b, so I would love to write a in terms of b, so I'll write 2 into, and this is 2 minus 2b plus 3b minus 6, that gives you 4 minus 4b plus 3b minus 6, that equals minus 2 minus b. And if this is the case, then I can write minus of 2 plus b. B is positive, this is negative, so this becomes negative. So we have got our first victory. So look at f1 and look at f5. So what we have proved is that f1 is positive. How much that is does not matter. And f of 5 is negative. So once you prove that f of 1 is positive, f is negative, using Bolzano's theorem, so using Bolzano's or intermediate, whatever you name it, or I will say IVP, intermediate, I love this term, intermediate value property for continuous function, we can say that this f indeed have a root x naught that belongs to 1 comma 5 open. So there is something here such that f of x naught equals 0. Eh, Now, okay. So next, let me do this one, that the other case is b is 0. This we can quickly finish. If b is 0, then f of x gets determined. So if b is 0, look at the case. If b is 0, then a becomes 2. So you get, this is 2 root x minus 1. And then you are getting minus of twice x squared minus 3x plus 1 square root. And then this must be 0. This must be 0. And if this is 0, then you will get root x minus 1 equal to root of 2x squared minus 3x plus 1. Now this number will become x minus 1. So this was 2. So 4 times x minus 1 equals 2x squared minus 3x plus 1. That is x minus 1 and times 2x minus 1. You get either x equal to 1, or you get 2x minus 1 equals 4. So x is 5 over 2. That of course belong to 1 comma 5. Now b less than 0, so we can take f of 1 is again b in the third case, b less than 0. And f of 2 I will write, that will give you a plus b root 3 minus root 3. So that is again 2 minus 2b plus b root 3 minus root 3. I can take the common and I will get 2 minus root 3 minus 2 minus root 3b. That will give me 1 minus b times 2 minus root 3. And that number 2 minus root 3 is positive, b is negative, so this is still positive. So ultimately f of 2 becomes positive. So that tells you that it has a root between 1 and 2. This f has a root between 1 and 2. And because 1 comma 2 is a subset of 1 comma 5, that tells you that f has indeed a root in f has a root f has a root in 1 comma 5 also. So let me review. So this was the problem. Fx is this much and a plus 2b equal to 2. So we are writing this. So I did casework on b and I found that f1 and f5, they all were created. And so I wrote b positive, then b negative, and then b equal to 0 was in the middle term, and that was easy one. That gets determined. So we found in each case that f1 and some other number product is 0. And so we know that this has got root always in 1 comma 5. So let me now share this screen again, or stop sharing. And okay, so we covered a lot of examples today, and they were really more charming and challenging than the studies. So now tomorrow there is a new lecture coming up, so stay tuned. Okay, that's all.